So today we are doing a problem 1483 Kth Ancestor of a tree node. So it's basically what it sounds like. We get a tree given by some parent array, and then we get like 10 to 4 queries which ask us to get like Kth Ancestor node or -1 if there is no such ancestor. Now immediately with number of queries, the problem is that you cannot just linearly scan up by parents because that's too slow. But what we could do is, if I computed first parent, which we have, then we could compare every second parent, which we can compute by getting parent of my parent, right? And then to compute the fourth one, we get the second parent of, so we get like a second parent of second parent if there is such, right? And suddenly we can, if we want like fifth, we just get the fourth parent of the node, and then we get first parent because in binary it's 101, right? So 4 plus 1, so we get first fourth, we jump 4 levels, and then we jump by 1 level and we are there, and that's basically it. Technically this is from LCA, so you don't have to, you should not be expected to come up with this yourself, and for sure not in interview, and for sure nobody will ask this in interview ever, I think, but whatever. But the point is that wait a second. Okay, now you might hear me better. So the point is that the point is what? The point is that if we want to do this in O1, we would have to do a lot of mental math. I can explain that approach at the end of the video once we submit this log n per query, but it's possible with ON, even pre-processing. We could theoretically do O1, but whatever, it's gonna be, for sure somebody did it in solutions, but you can see there is not even a tutorial for that. So let's compute the parents. So for each vertex, how many? That's n nodes, so we want like self n is n, self l is log 2 of n. Does that work? Yep, I guess that works. Let's see. So it's 7. Fair enough. So we could do like int and then +2 here, why not, right? And then we have to pre-calculate the parent. So parent is -1 for j in range self l for I in range self n, right? And then for p for I in range n. So basically we said the at 0th index should be direct parent, right? So 2 to power of 0, right? So PAR of VI is like a 2 to the ith parent of vertex V, right? So first we set par, let's do vertex of 0 is parent I, right? Or parent V. And then okay, so 0 is root, doesn't matter, right? And then for L in range 1 to self L, we do this, right? So So if parent for v in range n, right? And now for each vertex we do if parent of vertex l minus 1 is not minus 1 and parent of l minus 1 is not minus 1, then parent of v of l is equal to parent of parent v l minus 1 l minus 1. Now this should work, right? So the 2 to the lth parent is 2 to the l minus 1th parent of 2 to the l minus 1th parent, right? So that technically should work, we will see. So let's see, so Kth Ancestor, well, we need to go in binary, and I guess let's go like this. So vertex, so we got a node, and then for L in range self L minus 1 like this, right? And now if K and L K and 1 to L, then K minus equals 1 to L. Okay. I mean, we don't technically have to subtract, but whatever. So if node doesn't equal minus 1, then node is parent of node at level L, and then we just return node. And this should be self parent, and this should be self, and now everything I have to rewrite to common mate. Luckily Leetcode has this. Where is replace? Replace. Okay, don't replace. Let's see. Oh wow, that worked. There's no way I get this first try. Damn, I'm good, bro. Ha! Okay. Okay, I guess, and now I'm 11%. Which means that maybe we can cut this down by 1. Okay, we'll be 20% now. Maybe we can still do it with this. Okay, that won't pass, so plus 1. 24%. Okay, now let's see the O1 solutions. Yeah, they have early termination, I guess. I guess that helps. No, it doesn't. Okay. Who cares? Whatever. So, I mean, okay, nobody is talking about the O1 solution. Oh well, I guess. Okay, whatever. Nobody does O1 for some reason. Okay, so binary ladder O N log N login query o login. Okay, intuition. Instead of answering each query by going up the tree in with jumps of 1 naively, we can jump in powers of 2. Approach. K has a binary representation. Which allows us to split the jumps into powers of 2 based on what bits are on in the K. How do we calculate? Can we calculate 2 to the ith parent for all nodes for all I 0 like I less than LCL RCL, and here we do like log 2 of n. Yes, we just pass from we just need to compute the table parent vi for all nodes v. Yes, we just need to compute the table parent vi by increasing I, the 2 to the ith parent of v is just 2 to the I minus 1 parent of 2 to the I minus 1 parent of v maybe I was just thinking maybe you cannot do the O1 approach, but whatever. 2 to the ith parent of V is just 2 to the ith parent of the 2 to the ith parent of V. Parent Vi is equal to parent of, that's weird, so it's like I minus 1 parent of Vi minus 1. I think this works. Okay. Then to answer queries, we just jump based on present powers of 2 in K until we can, or we until we cannot anymore. O n log n initialization, since we calculate whole n log n large table, each cell in O1 using already calculated tables for smaller I, and O log n per query, since we just do O1 jumps for at most, we just do O1 jumps, of which there are at most O log n, the number of bits in mode, O n log n, since our parent table has that size as already mentioned. Okay. Okay, I guess see you tomorrow.